And that is a step 1 until step 10, the 2 hours. So once you understood it well, obviously you need to ensure that you are still understanding it at the same level of what you have understood. Because we as humans, we tend to forget some of it over time. And that is the revision method that I taught you, right? If you still remember the revision method. If you don't and you want to learn again, then let me know. All right. So let's start. Today is a gravitations for Xingling. It is Form 4, Chapter 3. Right. Form 4 is equivalent to year 10 or grade 10. Right. So let's start with chapter 1. Step 1. Okay. Starting time. Start time is here is 6 zeros. Right. So step 1 is create drawers. We have 5 drawers that we need to create over here. We have, oh sorry, this is, I got the wrong notes. Let me just open the right note. Sorry. This wave. Right? Okay, let's start again. Step 1 is create drawer. We have 5 drawers over here. Newton law, gravitational acceleration, Kepler's law, man-made satellites, and escape velocity. Right? So if you have a pen and paper, write it down, and also write down the story, because this will help you to remember the name of the drawer in sequence. So what is the story that is helping you to remember this in sequence? Just imagine there is this guy called Newton, a scientist called Newton, and using a strong gravity to pull Kelly into the man-made river. But then she escaped, right? So if you can put that story in your mind, and let me just help you to remember it better by showing you the story. Yep, this is the one.
Form 4, Chapter 3, Gravitation. Newton, using strong pull Kelly into man-made lake. She'll escape. Draw 1. Newton law. F and GF ran 2 kilometers away.
Wait.
Tie
Something is
centipede
not right.
and spin it in heavy orbit. Draw 2. Gravitational acceleration.
I'm not sure whether you are able to see the watch the video just now. Let me try again. Right, I'm going to start again. So I'm going to start now.
Form 4, Chapter 3, Gravitation. Newton, using strong gravity, pull Kelly into man-made lake. She'll escape.
Okay. I hope both of you are able to see or able to watch the very short clips. Right, show of hand if you are able to watch it and listen to what the gentleman was saying. Can you, Xingling and Aiden? Yes, you can. So I think Aiden, you should be able to see it with no. Very laggy for you. Okay, let me try again. Okay, I'll start again. And this is the main story, okay? If you see the scientist.
Form 4, Chapter 3, Gravitation. Newton, using strong gravity, pull Kelly into man-made lake. She'll escape.
Okay? So if you are not able to watch it clearly, then you can just do your own imagination that there is this scientist called Newton. It's laggy for you too. All right, okay. So let me tell you let me explain to you from using words. So there is a scientist called Newton. He has a strong equipment like gravity, like a magnet or gravity, to pull Kelly, and then pull Kelly into a man-made lake. Then Kelly escaped. Okay, this is to illustrate this story. Newton using strong gravity to pull Kelly into a man-made lake. She escaped. So first drawer is Newton law, using strong gravity, which is gravitational acceleration. Then pull Kelly. Kelly is Kepler's law, right? Kepler's is not a common name, so Kelly I think is more of a common name. That's why I use Kelly. If you have friends name starting with K that is helping you to remember it easier, then you can put it there. Right? You can replace Kelly with something K. Then pull her into a man-made lake. So man-made lake, which is man-made satellite. And then she escaped. Okay. This is not the right one. Let me put it back. Yep. Okay. Yeah, I hope you are able to remember this drawer in sequence. Now, let's go to step 2. Step 2 is this part over here. Okay, you can focus on the right-hand side. We have 5 drawers. So this step 2 is breaking down into 5 drawers. You have Newton's law, gravitational acceleration, Kepler's law. This one is a satellite. Man-made satellite. Oops. Right. Then drawer 5, you have escape velocity. Right. So let me just pull out my clock. Let's do the same drill. Right. For drawer 1, we'll take let's take 1 minute to read it, but read it slowly. Let's start now. Drawer 1. Don't worry, you do not fully understand this as of now. Just read it to understand the 4 points. That there are 4 points here. Okay, time's up. Right. So imagine now from the scale of 1 to 10, your understanding about this chapter, you are at about 1 to 2. So which is the lowest level. So this is to reflect when you read this part, we are not expecting you to fully understand it at the level of 10. And you should not be having this expectation as well. Right. So to give an assurance that even after reading this, you did not fully understand what is it about, this is fine. And this is normal. Right. You just need to know that in Newton's law, drawer 1, there is this formula. You're going to learn this formula later a bit more. And then there is this example. Then you have something called centripetal force. Right, sometimes centripetal force. And then you have this formula to calculate the mass of the planets. And that's it. Right. So you should be expecting your understanding level increase from 1 to 2. Only 2. The level 2. Right? For drawer 1. For drawer 1. Drawer 1 is just part of the entire chapter. Right. Then we'll continue to draw 2, 3, 4, and 5. And you should be expecting your level increase from 1 to 2 for drawer 2. And 2 is it's still a low level. So if I have to put it into perspective, out of 10 questions, you can only manage to answer 2 questions correctly, right? So out of 100%, you're only getting 20% or even 10% or even lower. So that is the expectation that you should be setting for yourself in terms of understanding the chapter at this point of time. After 2 hours, then you'll be going to a higher level, right? So don't worry, we just started 10 minutes ago. So now, let's do drawer 2, also 1 minute, right? Let's do drawer 2, also 1 minute. Because this chapter, I think, is quite, it's not an easy chapter. Let's put it this way. Okay, drawer 2, 1 minute. Okay, time's up. So we'll go through this, the remaining of the drawers quickly. So let's do draw 3 and 4 in 1 minute. Thirty seconds. All right, let's do 5, and whoever who wants to continue reading the remaining of the drawers, let me just maximize it. Right, I'll give you 1 minute to read drawer 5 and the remaining. All right, I'll keep. Okay, there are quite a few scary formula, right? For example, this one, this one, this one, this one, right? There are quite a few scary formula, especially this one. Don't be worried about the formula to be able to understand it fully now, because you are not expected to do that, right? We will going to have this, you understand the formula better as we go along to the following steps. Now you are still in step 2. So what you should be expecting is your understanding level increase from 1 to 2 for all the drawers, right? So there's a bit of understanding increase compared to what time did we start? Compared to about 10, 14 minutes ago, about 14 minutes ago, right? We started at 6:03. Now, let's proceed with step 3, right? So this step 3, drawer 1, you should be expecting your understanding increase from 2 to maybe 3. So how should you read this? If you realize there are 4 key points over here, and these 4 key points, if you compare to step 2, it is exactly the same. The only difference here is step 3 is having more explanation. So obviously, by reading more into the detail of each of the points, your understanding for drawer 1 should increase from 2 to a level that is higher. Let's hope you can increase to 3. I'm not expecting you to, or you should not be expecting you to increase from 2 to 10. 2 to 3, and that's it. 2 to 3. All right. So let's read this for 3 minutes. Let's do 2 minutes. All right, let's do 2 minutes for draw 1. Let's start now. All right. Okay. 2 minutes done. So you should be expecting your understanding level increase by a little bit, right? You should know a bit more about the formula. What is the important point is this is to calculate the gravitational force between two bodies. What are these two bodies? It's not your body, it's not your friend's body. Mainly, we are talking about two planets, right? Earth and Jupiter, Earth and Sun, Earth and Moon, or Jupiter and Mars, right? So we're talking about these two bodies. And what is the relationship between the forces between them with their mass and also with the distance, right? And that's all you need to know. If you understand at this to this level, that's good enough. Then same goes to point number 2. It's giving you some examples, right? And then centripetal force. Centripetal force is just like mentioned over here. If you have a rubber stopper and you swing it on a string, and that string tension is the centripetal force. It's a centripetal force. So the Earth is also having a centripetal force, but there is no string attached to it. So it's equivalent to like a centripetal force in the Earth. Okay, then calculating the mass, planetary mass, right, using the centripetal force and gravitational force. Now let's continue to drawer 2. I'll give you also 2 minutes so you can take your time to read. And in case you need to revisit drawer 1, then you can do it if you have more time after finishing drawer 2. Let's start now. Twenty seconds. All right. Now let's continue. Okay, let me give you some brief explanation. What is this? So the first point, which is exactly here, right? You see this one on step 2 is only one sentence and a few words. This one has a little bit more words, but they're explaining the same thing, right? How do you calculate the gravitational accelerations? Okay, if you do not understand what is this G, M, and R, for now it's fine. All right, G is a gravitational constant. M is the mass of the object. For this case, could be Earth. If you want to calculate the gravitational acceleration of the Earth, right? Then R is the distance from the Earth center, right? From the center of the Earth. You see, I'm explaining exactly as what is written over here, right? I'm not explaining more than what you have read. Then point number 2, there are two parts over here, below the surface of the Earth and above the surface of the Earth. Now you are standing on the surface. Below the surface means if you dig deeper into the Earth, let's say you dig 10,000 meters into the Earth, then the gravitational force, gravitational acceleration, which is this G, is changed, is lesser. So now if you are standing on the Earth, your weight is 50 kilogram. If you dig down, let's say 10,000 kilometers into the Earth, your weight is lesser. It's not 50 kilogram, could be 40 kilogram, right? Above the Earth is also the same. You go up, you'll be lesser, right? You go up, you'll be lesser. If you stand next to the satellite, you are no longer 50 kilogram. You could be 49 or 48 or 47 kilogram, right? There's a way to calculate it. How to calculate it? Don't worry about that now. You just need to know the concept. Right? Then the Earth, the gravitational forces is also having an impact on human body. Right? So let's continue for drawer 3, but this time, since you have warm up, I'll give you 1 minute. Right? So it's the same. You have 3 laws: first law, second law, and third law. Let's start now. Ten seconds. All right. Let's move on to drawer 4. Right. Let's move on to drawer 4. So drawer 4, you have satellite, man-made satellite. Man-made satellite. And there are 3 important points over here. 3 or 4 important points. I'm sorry. Right. So it's the same format. Here on the right-hand side, step 2, you have 4 important points. Step 3 on the left-hand side, or on the other side, you have 4 important points, but just more explanation. So let's start now. 1 minute. Ten seconds. You should be on point 4 now. All right. So this is the man-made satellite. Escape velocity. What is escape velocity? So there are 3 key points over here. So let's do also 1 minute. If you realize I intentionally leave some parts from the previous drawer on the page. So in case you finish reading this in 1 minute, you still want to reread what you have read just now on the previous drawer, then you can do that. Let's start now. 1 minute, drawer 5. All right, time's up. I hope by now you feel that your understanding level increased from 2 to 3 for all the drawers, right? 2 to 3. Let's continue on step 4. Step 4 is read FAQ, frequent asked questions. And there are 2 questions per drawer. So in total, we have 10 questions, right? So how do you read this? You have the question 1, and then you have the answer, and then you have the so what. So what is to basically to tell you why this matters to you. Why this matters to you, right? So you have this question 1, then you can also refer here. This question 1 is from which points, right? This question 1 is from which point? Obviously, this is point 1, right? Point 1 is talking about point 1. So by reading this, I hope you'll be able to understand what this formula is about, right? In more detail, right? So let's read this part here. There's a small introduction about what you are going to learn in draw 1. So let's take 2 minutes to read question 1. 2 minutes to read question 1. Let's start now. One more minute. Thirty seconds. Ten seconds. All right. So question 1 is one of the 2 questions in draw 1. So if I have to quantify your understanding level, by now it should be 3.5, right? From 3 to 3.5 for draw 1, right? Once you finish question 2, hopefully you feel that you also understand it a bit more, and you increase to the level 4. Level 4 is still a low level, right? Out of 10 questions, we are expecting you to answer 4 correct questions, 4 questions correctly, right? Out of 100 points, 40 points or a bit below, between 35 to 40 points, right? So don't set a high expectation for you at this point of time, right? So let's continue. This question 2 is about centripetal force. It's here, point number 3. Okay. So let's do 1 minute. I think much for 2 minutes. Let's do 1 minute now. Question 2. 10 seconds. All right. I hope by now at the level 4, understanding level 4 for drawer 1, you should be more confident on what is this formula about, and also what is this centripetal force about, right? Compared to 30 minutes ago when you started this, and when you read this for the first time, you have almost no idea what is it, what you have read. But by now, at level 4, you should have more understanding about drawer 1, right? So let's do the same drill, but now for drawer 2. For drawer 2, I'll give you 2 minutes because it has included this small part here to introduce what is drawer 2. Right, 2 minutes starting now. Fifteen seconds. All right. So by now, your understanding level for drawer 2 should increase from 3 to 3.5. Now let's go to what is it? Which point does it explain? Explain the point 2 and point 1 here. All right, point 2 and point 1. All right. So for question 4, the last question for this drawer, it explain the last point, the human growth effect. All right. Let's do 1 minute for question 4. Let's start now. Twenty seconds. Ten seconds. All right. So let's continue on drawer 3. Right, drawer 1 and drawer 2, if you still remember the name of the drawer, is drawer 1 is Newton law, drawer 2 is gravitational acceleration. Right, in the story, you remember the scientist called Newton? He is pulling someone using gravitation, using a strong gravity. Okay, Newton, strong gravity. So draw 1, draw 2. Pulling who? Pulling Kelly. Kelly represents Kepler's law. All right. Now, if you see draw question 5 and question 6, question 5 is talking about Kepler's first law and second law. So first law and second law. Then question 6 is talking about the third law. Right. So let's read this entire part in 2 minutes. Let's start now. So there's 1, 2, 3 laws. Thirty seconds. All right. Drawer 3. So drawer 3 is quite simple, I would say. Is Kepler's law, and Kepler's law, there are 3 laws. The first law is basically telling you that the planet is moving in elliptical orbits. So it's not a round circular orbits, it's elliptical. Elliptical is like an oval, right? And having the sun at the focus, not at the center, but at the focus, right? That means at the side of it. The second law is talking about this planet moving faster when it's closer to the sun. Yeah, I know this law of area is a bit confusing, but for now, you just need to know if you are a planet and you are circling in the orbit around the sun, when you're nearer to the sun, you run faster. Then if you're away from the sun, you run slower. That's second law. First law, the orbit is not circular. The orbit is not like a circular shape, like a round shape, right? Like a circle. It is elliptical, right? Third law is talking about the relationship between the orbital period and also the orbital radius, right? Orbital period and orbital radius. Obviously, if you are further away from, for example, the sun, then the time is needed for you to complete one round is longer. Right? For Earth, we need 365 days, which is 1 year. For planet that is further away from us, some of them takes hundred of years or tens of years from the definition of Earth to complete 1 year. Yeah, because we are further away, right? And that's the relationship. Okay, I hope your drawer 3 understanding now improve or increase to level 4. Let's continue for drawer 4. Okay, drawer 4 is man-made satellite. So remember the scientist Newton pulled Kelly into a man-made lake. So man-made satellite. Right. So let's do this one drawer in 2 minutes for 2 questions. After FAQ, we will take a break. $30. All right. Last drawer before we go for a break. Now, escape velocity. Escape velocity is the velocity that you need, or the speed that you need to go out of the Earth. When you are out of the Earth, you are going into the universe, and you forever not coming back again. So what is the minimum velocity that is needed for you to go out of the Earth and never come back again? Right? Sounds scary, but it's very difficult for you to go out of the Earth, right? Because your speed that is needed over here is 11,000 meter per second. 11,000 meter per second. Right? I'll give you some context over here. The speed of the sound is 320 meter per second. Sound. Speed of the sound. And this is much more than the sound. Right? 11,000 against 300. All right. So it's not easy to get out of the Earth. Just to put this thing in perspective. All right. So let's do 2 minutes for drawer 5, and then we'll go for a break. And now with the intention to improve your understanding from 3 to 4 for drawer 5. And that will complete the whole 5 drawers. Let's start now. All right, time's up. So far, I hope you are able to feel that your understanding increased from 1 to maybe 4. Right, it has been quite a heavy reading. Let's do a 5 minutes break. Let's go for a toilet break and water break. See you later. All right. Can I have a show of hand if you are all back? Yes, Aiden is back. Xingling, are you back? Yes. Yes. Just now the lagging video, I think there's a solution. The solution is I will send you the link here. Let's see whether it's lagging. If you open it from your side, you can try. You can try to open it from your side. I'll give you 1 minute to test it out while I'm preparing for the next steps. Aiden, you write something. Could running on a track be a good example? Like if you're on a closest track, it's easier. Okay, let me finish the timer first. Right, to answer your question, it is not like running a track. Okay, if you're talking about second law is if you are, let's say I'm the sun and you're the earth, and you are running faster when you're nearer to me. Because it is elliptical, so at a certain point you are further away from me. And when you are further away from me, you run slower. Maybe you can see it this way. I'm a very strict coach to train you on running. When you are nearer to me, that means I can see you clearer. And I see you that whether you are running to the highest speed that you can or not. So you run faster. And you are further away from me, I cannot see you. Then you try to run slower. Okay? So the speed changes. That is second law, Kepler's second law. Okay? So I hope you are able to open this video. And the first part is to describe, is to tell you the main story. Right? Newton's using strong gravity pull Kelly into a mimic lake, and she escaped. Now, are you able to open the video? By the way, can I have a show of hand if you can? Yes. Okay. And I hope there's no lag, right? Because of maybe you open it directly from the link is better, right? That video is consisting of all the stories. The main story is the first part. Then the following is the drawer 1 story, 2, 3, 4, and 5. Right. That is in step 6. We'll go through that step 6 a bit later. Now is step 5. Now, maybe we can try something new. Okay, since you already opened that video, let's open that video together. Right, let's open that video together. Let's see, I'll play the video on my side. You also try to play the video on your side and watch drawer 1, the drawer 1 video. Let's watch for a few seconds.
Draw 1. Newton law. BF and GF ran 2 km away. Tie centipede and spin it in heavy orbit.
Right. So drawer 1 is talking about BF, boyfriend and girlfriend. They are running 2 kilometers away. Why boyfriend and girlfriend? You remember that formula where they are calculating the forces between 2 planets. So they are attracted to each other. So boyfriend and girlfriend, usually they are attracted to each other, right? So this is to reflect the 2 planet, the mass of the 2 planet. And why 2 kilometers away? Because the distance is at the square, and also the distance is at the square. So r to r square. So I use 2 kilometer to represent the square, and distance represent the r. R is the radius, right? And then what was the story again? And then the spin centipede. Centipede is like, sounds like centripetal, right? Centripetal. And this centripetal force is the invisible force, like you are spinning the rubber stop on a string that's strung on that is attached to a string, right? So this is to help us to remember what is the key information in the drawer 1, right? See, drawer 1, you have this formula which is about the boyfriend and girlfriend, and also the 2 kilometer distance. Then you have the centripetal force, which is I'm using the centipede to help you to remember there is this centripetal force that you need to understand, right? Okay, so let's go to drawer 2.
Draw 2. Gravitational. Acceleration. Travel under and above Earth. Became small lung and low blood pressure.
Right, drawer 2 is travel under and above the Earth, and then became small lung and low blood pressure. So it's talking about the gravitational accelerations. So there's this variation of G. G is gravitational acceleration below the Earth and above the Earth. So you saw that the black character, he was traveling from below the Earth to above the Earth, and then then became small lung and low blood pressure. This is to illustrate that there is this points. There are these few points that you need to know that is important in drawer number 2. Okay, let's go to drawer number 3.
Lung and low blood pressure. Draw 3. Kepler's law. Elliptic ran faster when nearer to Sun. Ran 3 laps in 2 seconds. Draw.
Right. So elliptic is the man's name. Elliptics, it run faster. So elliptics, the man's name elliptic is to illustrate Kepler's first law, right? Then the second law, it says that it runs faster when it's closer to the sun. So it runs faster when it's closer to the sun. That's the second law. Then the third law is talking about he ran 3 laps in 2 seconds. So that is the relationship between the orbital period and orbital radius, right? Period is time, which is t. Radius is r, which is distance. So 2 laps means distance, or 3 laps means distance in 2 seconds, right? So this is to help you to remember the content that you need to know in drawer number 3. First law, third law, second law, and third laws. So let's move to drawer 4.
4. Man-made. Satellites. Newton ran fast and freefall into Earth. I likes geography.
Okay, I like geography, not likes. Hey, where is it? Right. So drawer 4, Newton free fall. Right. It's talking about satellite has been free falling into the Earth, but keep failing. Right. This is the concept of why the satellite is keep orbiting around the Earth. Okay. And also I like geography. Why geography? Is to reflect on this. There are 2 types of satellite, geostationary and non-geostationary. So the geography, the geo, is to help us to remember there are this satellite, different type of satellite. Fixed position satellite, which is geostationary, the moving satellite, which is non-geostationary. Right. So let me just explain a bit here on how do you able to understand this satellite movement. So imagine now you're having 2 stones. You're holding one of the stones on your hand, and you throw in front of you. You throw it right in front of you. The stone eventually will fall down on the earth, on the ground, right? You take another stone. the second stone. You throw harder, right, with a bigger strength. Then the stone will go further, right, compared to the first stone. So the first stone landed somewhere nearer to you. The second stone landed somewhere further from you, right? Imagine if you throw this stone so fast that it doesn't land. It doesn't land on the earth. Why? Because earth is like a curvature. Earth is not a flat. It's not flat. It's like a curvature. So the stone will keep falling on the earth, but it failed because the earth is a curvature, right? And because there is a centripetal force, it holds the stone around the earth forever, as long as the speed doesn't change. It is traveling at that speed, and it keeps failing from falling on the earth, right? And that is the concept of satellite. Why satellite doesn't fall into the earth? Because satellite keep falling down but fail to fall on the earth because the earth is a curvature in shape, right? So I hope this can help you to understand this a bit more. Now let's go to the last drawer, escape velocity.
Draw 5. Escape velocity. Ran at high velocity. To escape and breathe air.
Okay, run at high velocity to escape and breathe air. So this is the minimum velocity that is needed for you to escape from the earth, which is this one, 11,000 meters per second. Why breathe air? Later you know, okay? Because why our earth is having atmosphere which trap the gas? Because the gas is not having the velocity of more than 11,000 meters per second. So they are all trapped in the earth, in the atmosphere. So that is the story of I need to breathe air. Air represents the atmosphere, right? So this, let me just pull out. Okay, right. So this explains the story. This explains the story. So let's continue on drawer one for step 5. So now you can imagine in the story we have what in drawer 1? We have the boyfriend and girlfriend, right? The boyfriend and girlfriend, and with the centipede, right? With the centipede. So let's do this for, let's see how long is it. Okay, we'll break it down into 2 parts. Let's read here until here for 1 minute. Let's start now. All right, 1 minute for now. All right, this part here is this formula, right? Remember this formula, that the scary formula maybe 1 hour ago. Now it becomes less scary. All right, I hope it becomes less scary, because now you know that this formula, what's the relationship between the G, the M1, M2, and also R. By using that story, boyfriend and girlfriend 2 kilometers away, right? And they're attracted to each other. Boyfriend and girlfriend, they're attracted to each other, right? So I hope now you should have this intention to increase your understanding level from 4 to 5. So you should be going into that path, that directions, right? To 4 to 5. Now you should be at 4.5. Okay, let's do this for 1 minute until the centripetal force. All right. All right. So let's continue on this part. Another 1 minute. Let's start now. All right. So your understanding on drawer 1 should become near to 5. 5 is still not high level, so don't set high expectation for yourself as of now, but near to 5. So let's continue drawer 2, which is gravitational acceleration. Let's see how long is this. It's 2. Okay, wait, let's divide it into 2 parts here. Let's divide into here to here, right? And this one, let's do how many minutes? Let's do 1 minute. All right. Let's continue the last part here, the human body. Human body here, this part here, right? Let's do 1 minute for the table. Right, that's drawer 2. Drawer 2, increase to 5. Drawer 3, let's try and let's feel that you are able to increase from 4 to 5. Drawer 3, 1 minute, let's start now. All right, here we go. I hope you have the same feeling. By now, your understanding level increased compared to what time did we start? 6:03. That means maybe 1 hour and 20 minutes ago. Right, your understanding level on this chapter should increase from 1 to maybe about 5. 5 is only 50%. So if you do not understand fully, it's still fine. So let's break this into 2 parts. Until here for 1 minute. Drawer 4. Okay, I'll put it over here. Oops, where's the clock? Yeah. Hmm? Okay. All right, let's continue the last part here for also another 1 minute. Let's do it now. Okay, now we are on drawer 5. We are almost there. The hardest part, which is 1 to 5, step 1 to 5 is almost done. All right, let's do 2 minutes. a bit more relaxed. Drawer 5. Ten seconds. All right. Step 5 is done. Now, step 6, we have already done a bit of step 6 just now. A bit of step 6 just now. So let's read this quickly. Right. Drawer 1, you have this boyfriend and girlfriend. Ran 2 kilometers apart and tie centipede and spin in a heavy orbit. Heavy orbit, why heavy orbit? Because I'm trying to reflect the mass. Mass is heavy, right? Kg, kilogram. Then boyfriend and girlfriend, I think I already explained this. They are attracted to each other. 2 kilometers away is to talk about the R square. Square is 2, right? So 2 kilometers away. And then drawer 2, gravitational accelerations, okay, is somebody, and for this case is that black body, travel under the earth and then above the earth. And then his or her, or it, let's name it it, small lung, became small lung, the lung becomes smaller, and low blood pressure. Then you have this Kepler's law, right? Elliptic is the man that ran very fast. His name is elliptic. He ran faster nearer to the sun and ran 3 laps in 2 seconds. Then man-made satellite, Newton ran fast and free fall into the earth. This is to explain why the satellite doesn't fall on the earth. Right, then I like geography, right? Because that is to link it with the geostationary and non-geostationary satellite. Then this escape velocity. Yeah, escape velocity with high velocity, you run at high velocity and breathe the air, right? If you can take 2 to 3 minutes to run that video, right? I'll give you 2 minutes to run the video. I think the video is only 1 minute. Let's start now. Right, run the video. I will not run from my side so that you can focus on your screen. All right, let's do. Okay, let me just enlarge this, make it bigger. This picture over here is to help you to is how I draw to illustrate the story. What you saw in the video, I put it into picture. I put it into picture. So let's look at the picture, this ugly picture, for 2 minutes again, right? So that you can see whether you are able to remember the story. Let's do that. All right. Now, I hope now your understanding increased from 5 to 6. Right, 5 to 6 is going well now, I hope. Now let's go to step 7. Step 7, we have 10 questions. We have 10 questions. And let's read the questions and then make your own answer before you read the answer. Before you read this answer, make your own answer. Then compare your answer with this answer. Let's do it slowly a bit for this. Let's do for the first questions. Let's do 1 minute, or let's do 2 minutes for 2 questions. Right, let's start now. All right. So by reading this, I hope your understanding on drawer 1 increased to level 7. You should be able to have more confidence, much more confident on drawer 1. Let's continue on drawer 2. Right, let's do the same thing. 2 minutes. All right. Drawer 2 up now, level up to level 7. Let's do drawer 3. Let's start now. Okay. Drawer 4, man-made satellite. 2 minutes, start now. 10 seconds. All right, last one, before we go to the easy part, which is to watch the video. Right, let's start now. One minute. Thirty seconds. All right. I hope by now your level has leveled up to level 7. Level 7 is a good level, right? And I hope that you also feel the same. Now we are at the end of the steps, step 8.
Okay, let's talk about gravity. It's this invisible
Okay, can you
force
see it and can you hear it? Can I have a show of hand?
dictates pretty much
Can you see and
everything,
can you hear?
from a single
Okay.
apple falling from a tree to the
All right,
grand
Singing
dance of
can,
entire galaxies.
I think Aiden also. Aiden, you can see and hear, right? If not, then you have to tell me. Right, we have, yes, 6 minutes, about 7 minutes. So now with this understanding about the drawer, 5 drawers, and each drawer is having their own story, I need you to relate what this lady is going to explain to you, relate to what you have learned over the past 1.5 hours. Right? Let's start now.
Okay, let's talk about gravity. It's this invisible force that dictates pretty much everything, from a single apple falling from a tree to the grand dance of entire galaxies. Today, we're going to break down gravity, the true architect of our universe. So, let's get things off with a puzzle that people have thought about for, well, forever. Why does an apple fall down, straight to the ground, but the moon just kind of hangs up there in the sky? It seems like they're playing by two totally different sets of rules, right? But as you're about to see, it's all the same game. And the person who cracked this cosmic code was, you guessed it, Isaac Newton. He had this absolutely revolutionary idea. The force that pulls an apple to the ground is the very same force that holds the moon in its orbit around the Earth. Mind-blowing stuff. So how in the world did he make that connection? Let's trace his thought process. We're going to start with that famous apple and zoom all the way out to the moon.
Drawer 1.
Newton figured out that this force really just boils down to two key things. First, mass. The more stuff you pack into an object, the stronger its gravitational pull. Makes sense. Second, distance. Gravity gets weaker as you get farther away. But here's the kicker. It doesn't just get a little weaker, it drops off super fast. It's kind of like the light from a candle. The farther you are, the dimmer it gets, and it gets dimmer really, really quickly. And this is where the pure genius comes in. Newton took all of this and packed it into one single, beautiful equation. This one formula doesn't just work for planets and moons. It describes the gravitational pull between any two objects in the entire universe. You and me, your phone, Jupiter, everything. That's why it's called the universal law. Okay, so that's the big cosmic law. But let's bring it right back down to Earth. How does this grand formula relate to something we all feel every single second of our lives?
Drawer
Our
2.
own weight. So here's the big connection. The force we call weight, which you probably learned in science class as mass times acceleration or F equals mg, that's just our local, everyday experience of Newton's universal law. They're two sides of the same coin. Your weight is literally just the gravitational force pulling you and the entire mass of planet Earth together. And since they're just two ways of talking about the same force, we can set the equations equal to each other. Now watch this. This is the cool part. The mass of the smaller object, you, an apple, whatever, is on both sides of the equation. So it just cancels out. This is amazing. It means if you ignore air resistance, a feather and a bowling ball will fall at the exact same rate, and with this one simple step, we can figure out g, the fundamental acceleration of gravity, for any planet out there. So, when you actually plug in the Earth's mass and its radius into that new formula, what do you get? You get this number right here, 9.81 meters per second squared. See, it's not just some random number they make you memorize in school. It's a direct result of our planet's size and mass, all figured out from a law that runs the entire cosmos. All right, now let's zoom back
Drawer
out,
3, the
because
three
we can
laws.
see gravity acting like a sort of cosmic choreographer for the planets. And way before Newton came along, an astronomer named Johannes Kepler had already figured out the basic dance steps. So first, Kepler realized that planets don't travel in perfect circles. Their orbits are actually ellipses, squashed circles or ovals. And the sun isn't right in the middle. It's off to one side, at what's called a focus point. Second, he noticed something really interesting about how fast the planets move. They speed up when they get closer to the sun and slow down when they're farther away. Think of it like this. To cover an equal-sized slice of pie of its orbit in the same amount of time, a planet has to move a lot faster when the slice is short and fat, and a lot slower when the slice is long and skinny. And third, he discovered this really elegant mathematical link between a planet's year, how long it takes to go around the sun, and its distance from the sun. To put it simply, the farther out a planet is, the much, much longer its year is. Okay, so let's bring
Okay,
it
drawer
back home
4.
and see how we've used all these cosmic rules to our advantage. I'm talking about the thousands of man-made satellites that are circling our planet as we speak. So how does the satellite stay up there without just falling back down? Well, here's a wild thought. It is constantly falling, but it's also moving sideways incredibly fast that as it falls, the Earth curves away underneath it at the exact same rate. Gravity provides that constant inward tug that keeps bending its path into an orbit, instead of letting it just fly off in a straight line into space. Now, this creates an unbelievably delicate balance. For any specific altitude, there is one and only one perfect speed that will keep a satellite in a nice, stable orbit. Go just a little too slow, and you'll spiral back down to Earth. Go a little too fast, and you'll break free from Earth's gravity and fly away forever. But what if flying
Drawer
away
5.
forever is exactly what you want to do? I mean, what if you don't want to just orbit? You want to leave for good. Well, for that, you have to break the chains of gravity. We're not talking about staying in an orbit anymore. This is about hitting a speed so fast that gravity can never ever pull you back. We're talking about escape velocity. And the number you have to hit, it's just staggering. To break free from Earth's gravity completely, you have to be going over 11 kilometers every single second. That's the barrier that every rocket has to break to send missions to the moon, Mars, and beyond. And as you can see here, this cosmic speed limit is totally different for every world because it's all tied to mass. It would actually be pretty easy to launch off the moon. But escaping the sun's monster gravity, that requires a speed that's almost impossible to even imagine. But Earth's high escape velocity isn't just about keeping us stuck here. It's the very reason we can live here at all. See, the air molecules in our atmosphere are all zipping around at about 500 meters per second. But that's nowhere near fast enough to escape Earth's powerful gravitational grip. Our gravity literally holds our atmosphere, our entire life support system, in place. So from one single falling apple, Newton's laws basically gave us the map to the heavens. They taught us how to stay here on our world and how to break free. Gravity is both the chain that binds us and the rails that can guide us to new worlds. Which leaves us with just one question. Where do we go next?
All right. We are running out of time, so I will not go to podcast. I'll go straight to our step 10, your favorite part, to test gravitational test. Give me create 10 MCQ to at a time without answers. All right. Excuse me. I'll keep this on the left. I'll pull out, as usual, I'll pull out. Where's my keynotes? Yes, yeah. I'll put out on the right. Okay. So let's do the same drill. Let's start now. Question 1, question 2, what is the answer? Let's do it a bit quickly because I'm running out of time. Okay, I'm waiting for you guys. Yep. Aiden, if you can type or you can speak it out, you can tell me your answer. It's fine. You can choose. Number 1, what's the answer? And number 2, what is the answer? Don't worry about getting it wrong. It's fine. It's actually good to get it wrong. Then you know this is the new information that you need to store it inside your brain drawer. One is C. What about Eden? 2. What about 2? All right. What about 2? Remember the boyfriend and girlfriend? The boyfriend and girlfriend, 2 kilometers apart. Remember that? Question 2 is A. What about Singling? Singling? Singling, are you typing? You want to try 2? A, B, C, D? Just try. Don't worry about getting it wrong. Question 2 is C. Okay, I think it's C because it is inversely proportional to the square of the distance. Remember this formula? Directly proportional to the distance is not, because directly proportional means if the distance is increasing, the force is increasing. But the fact is, if the distance increase, the force decrease. Right? So let's try A and ask GPT to provide us the right answer. Right? So what is the right answer? So Aiden, you can and then you can read this quickly. Okay, good. No problem. Don't be sorry about wrong answer. It's good to have wrong answer. So now you can understand and remember this better. So let's continue. Drawer 2. What is the value of gravitational acceleration? C on Earth's surface. B and C. Okay, what about 4? Gravitational acceleration on Earth's surface. Question: what happened to G when you move further away from the Earth? Move further away from the Earth. What happened? C. Singing also C. Good. Okay, for question 3, C is gravitational constant. Okay, gravitational constant. Gravitational acceleration is 9.81. Right. So let's intentionally make it to the wrong one, so that we'll have more explanation. Okay. So this is the this is the explanation. So Aiden, just take note. All right. I hope you finish reading it. 1, 2, 3, 4, 5. Okay. Let's move on. Move on to 5. Drawer 3, Kepler's law. Remember the 3 laws, okay? Now, the story is the elliptic running faster near to the sun, and how many? 2 leap in 3 seconds. According to Kepler's first law, B, right? Okay, that's first law. Excellent. Good. D, what about Aiden? According to Kepler's second law, yes, it's D. Excellent. Now we got it right. Excuse me. Okay, 7 and 8. Let's do it. Man-made satellite. Remember, the Newton was falling down, running so fast and falling down on the Earth. Then say, I like geography. What provides the centripetal force for satellite orbiting? 7 is C. Also C. Great. The formula for centripetal force. Look here, right? On your left. On your right. Which formula is for centripetal force? Oh no, centripetal force is here. This is row 1. Right, B. Right, Aiden, I think it's B, right? Oh, right. One more set, then we are done. Okay, 9 and 10. Escape velocity. Let's throw up to see the speed required to escape velocity is the speed required to if an object is launched with speed less than escape velocity, it will okay 8 no question 9 and 10. Anyone? 9 is C from Sinling. 9 is C from Aiden. 10 is C from Sinling. What about Aiden? Also C? Excellent. I think it's correct. Good. So I think now your understanding level is at 9. Right, like I say, you want to, if you're given a choice, you want to maintain this understanding level. rather than reducing it, right? But we as human, we will not be able to remember everything over time. So how to do that? How to do that is the revision steps. Revision step is you need to quickly go through the story of each drawer, and then hoping that that drawer story is able to trigger you to remember and to understand what is in each of the drawer in the chapter, right? And that is this part here, revision step, and that needs more frequent 10 minutes, because this one maybe will take only 10 minutes for each round, right? So maybe every day or every 2 days you do it once, and that's it. Okay, thank you very much. I hope you learned something today, and see you next week. Bye bye. Bye bye. Bye bye, Singling. Bye bye, Aiden. You're most welcome.